Okay, here's the next part of our studies in physics. This is on scientific inquiry. This is kind of a long chapter, but we should get through it pretty quickly. It has to do a lot of stuff that you already know, and if you already know it, it's a good refresher. If you don't know it, it's a good lesson to learn along the way. So here is scientific inquiry. Objectives: know the definition of science and its strengths and limitations, distinguish between hypotheses and theories, explain the impacts of the scientific contributions of historical and contemporary scientists on scientific thought and on society. So we're going to cover all these in this today, all these topics. Again, we start with some assessment questions. State in your own words the definition of science. You see an icicle hanging from a branch or a roof and notice that the ice forms in ripples on the surface of the icicle. Which of the following is a valid way to test a hypothesis about these ripples? Do research for information on the internet, look for information in textbooks or a library, ask a teacher or an knowledgeable person, do an experiment by creating icicles at different temperatures. More assessment questions. Again, we'll look at these at the very end of the chapter. Which of the following could be scientific evidence? The speedometer on a car reads 57 miles per hour. A photograph shows the planet Venus at a specific position in the sky every evening. A newspaper headline announces the discovery of a previously unknown fundamental particle. You notice that the temperature outside is 27 degrees Celsius. A teacher tells you that the atomic mass of carbon is 12 grams per mole. Still more assessment. How did Penzias and Wilson contribute to our understanding of the origins of the universe? All right, these are the physics terms you're going to get in this chapter. Hypothesis, theory, objectivity, repeatability, experiment, and scientific method. These are key terms that you're going to need to know and write down because you're going to need to show me them in class tomorrow. All right, the nature of science. Science is the study of the physical world we talked about in the last chapter. Science, as defined by the National Academy of Science, is the use of evidence to construct testable explanations and predictions of natural phenomena, as well as the knowledge generated through this process. One of the key things here that I want for you to see, that it is testable. It's got to be testable. If it's not testable, it's just not going to be considered part of science because you can't prove it or disprove it. The nature of science continued. Modern science has a vast and evolving body of knowledge about the natural world. We describe this knowledge through models. Physical models. The Earth orbits the Sun. We can see this is happening. We used to think that the Sun orbited the Earth. We were able to disprove that through experimentation. Mathematical models. The force of gravity is given by the following equation. We can't see gravity, but we can see the effects of gravity. We can mathematically calculate what gravity is going to do. Conceptual models. The Sun is surrounded by a gravitational force field. Well, we can't see the gravitational field around the Sun, but our Earth is revolving around it. So there has to be a gravitational field there, the same way that the Moon is revolving around the Earth. So there's got to be a gravitational field. And so it's a conceptual model. So you have physical models, mathematical models, and conceptual models. All right, science, strengths and limitations. Some strengths of science is its flexibility. Scientific knowledge is subject to constant testing and revisions as new knowledge and new technology become available. Changes in science lead to an ever-increasing understanding of the physical world. We test things over and over and over again, and once we test them, we publish what our tests have found. And then other people repeat these tests and see if they get the same conclusions. So that's why it's tested over and over and over again until we come to some conclusion when multiple people have tested something. The limitations. Science is limited to the study of the physical, testable, observable world. It is limited to the natural explanations of phenomenon. There are a lot of things out there that we cannot test. One of the things out there in science right now is the string theory. Well, string theory is not testable. So we can't really put it in part of science right now because there is no test for it. So that's one of the limitations of science right now. Scientific inquiry. Physics is both a process and a body of knowledge. We have facts, theories, formulas, natural laws. We're going to go through all of this stuff in this chapter. Knowledge includes facts like the mass of an electron. So there's knowledge parts to this. This knowledge is gained through a skill-based process known as scientific inquiry. So we're now going to learn really what scientific inquiry is. All right, scientific inquiry. This is a process of proposing and testing potential explanations to discover which ones are true laws of nature. A scientist might find that when she shines light on a mirror at an angle, whatever, the light always reflects from the mirror at the same angle. If you look over to the side here, they have a mirror and they're shining light off of it, and you've got the same angle bouncing off on either side. This is called the law of reflection. If she tries this for different angles and mirrors, she will discover that it is always true. It is the law of reflection. As long as you're using a flat mirror, this is always going to be the case. All right, a hypothesis. A hypothesis is a tentative, testable explanation for observed physical phenomenon. You may have learned other, definitions for hypothesis, but this is the one we're going to be going with in this class. There are some easier ones and some harder ones. This one's kind of in the middle. Most hypotheses are incomplete or wrong when first proposed, like the Earth is flat. Hypotheses are still important because they provide something that can be tested and revised. So we once said that the Earth is flat, and we all now know that the Earth is not flat. Their hypothesis was that it's flat, so then you had to test that. You had to set sail and sail around the world and prove that it's not flat. So you actually had a hypothesis. Not every hypothesis is going to be true. But you have to be able to test that hypothesis for it to be a hypothesis. A theory is a comprehensive, well-established, and highly reliable explanation of a natural physical phenomenon. Basically, when a hypothesis is tested over and over and over and over and over and over again, and they keep getting the same findings from their experiments, it might become a theory. And then that theory will then be scrutinized over and over and over again, and then eventually it might become a law. An example, Newton hypothesized that light is a particle that bounces off a surface like a billiard board, or billiard ball, I should say. So over here you have incident light. Light is scattered in all directions. Others propose that light behaves like a wave. So here you see it waving out. So here you had a straight line and it bouncing around, and here you have light waves waving out towards the Earth. Neither hypothesis is completely correct. Both were combined to form a modern quantum theory of light. This is basically what the quantum theory of light says, that it behaves as both it'll travel in a straight line, but it also travels in waves. So it's both a particle and a wave. So there's a little physics for you. All right, theory versus a hunch. In everyday language, you might use the word theory to describe a hunch that you're having about something. A scientific theory is very different from your hunch. A scientific theory has been tested again and again against the harshest criticism and always comes up correct. The findings have repeatability. Other experimenters who test the theory always observe the same results. So sitting there and saying that you have a theory about something isn't necessarily true. You'll have a hunch about something unless you've had that hunch over and over and over and over again, and it's been tested over again to get the same results. The scientific method. The scientific method is the process of proposing theories and rigorously testing them. A tentative hypothesis becomes a theory only if the outcome of every single related experiment or observation made by multiple researchers agrees with the hypothesis. So basically, to turn a hypothesis into a theory, it's got to be tested over and over again. All right, and here's our little chart for the scientific method. You start out with a question, then you create a hypothesis about the question, then you make predictions, you test your hypothesis, you analyze your test, and then you draw a conclusion. And then you can repeat it all over again if it doesn't come out the way you thought it would be. And then you can make another question, change your hypothesis, prediction, test, analyze, conclusion. This happens over and over again for the scientific method. Any scientist that is doing any kind of testing, they basically follow this over and over again. Do these adjectives describe theories, hypotheses, or both? So I want you to take a minute, go through each one of these, and think is it a theory, a hypothesis, or both? You can pause the tape here to look at it because I'm about to move on. All right, these don't quite line up, but A, tentative is a hypothesis. B, testable is going to be both. C, capable of being observed or supported by experimental evidence would be both. D, well-established would be a theory. E, highly reliable would be a theory. Based on natural physical phenomenon would be both, and subject to change would be both. Impact of scientists on society. Some findings have broad impact on other scientists and on society. Each scientist builds on the results of others and in the end deepens our understanding of the universe. Let's look at a few examples. So what we're saying is what a scientist does is usually takes someone else's work and then replicates that work and then tries to expand on that work after that. That's why we're not doing the exact same experiments that Isaac Newton was doing so many years ago. We've expanded on that and we've learned from it. All right. We have Lemaitre, who proposed the Big Bang Theory. And from that, Alpher and Hermann predicted the universe's temperature based on that theory. Then Penzias and Wilson verified the predicted temperature from this theory. You can see the timeline. We started in 1927, went to 1948. Now we're in 1964. And finally, in 1992, Smoot and Mather measured variations in radiation that led to the present-day cluster of galaxies, now that we know that galaxies are everywhere. You see, each set of scientists were working on the evidence that was provided from the scientists before them. So scientific theories are subject to change as new areas of science and new technologies are developed. All right, near-Earth objects. A geological team found high concentrations of iridium in a rock from the time of the dinosaurs' extinction. So, only asteroids contain that much iridium. Theory, dinosaur extinction was caused by the impact from a giant asteroid. This is where we came up with our theory that an asteroid hit 65 million years ago down in the Yucatan Peninsula. Climate change. Many scientists are currently engaged in research about global temperature changes and rising sea levels. So we have the energy from the sun coming out. Societal impact. These findings have led to broad societal discussions about our impact on the Earth's climate. So just about because scientists are talking one way, it's having repercussions because then people are starting to talk about what can they do to help the Earth. Scientific analysis. In the process of building scientific theories, scientists must analyze, evaluate, and critique scientific explanations. Several tools for this. The tools for analyzing a scientific explanation. Observational evidence, as you observe things working in the world. This is big with psychology. They make observations and human studies and things like that. Logical reasoning. You can make the logical leap. If you do a small experiment in a lab, you can make a logical leap to a larger sized experiment that you can't hold in a lab. Experimental testing, and this is the basic one they mostly do, is they do testing over and over and over again in a laboratory. So observational evidence. Scientific explanations may be analyzed and evaluated through observational evidence. An example of this. Observation of the phases of Venus support the explanation that both Earth and Venus orbit the Sun. So they're able to look at how the Earth goes around the Sun and how Venus goes around the Sun, and they can both say, hey, both of us are going around the Sun, and the Sun's gravitation is pulling us around the Sun. The observation of Venus satisfies the criteria for scientific evidence. They are objective and repeatable. Logical reasoning. Scientific explanation may be analyzed and evaluated through logical reasoning. Our example. The explanation for the seasons is the Earth's rotational axis is tilted about 23 degrees. If you look at the little diagram to the right, shows you how the sun is, or how the Earth is tilted 23 degrees. How does this logical reasoning allow us to analyze this explanation? If this explanation for the reasoning is true, then it logically follows that an observer at noontime in Austin, Texas, 30 degrees north latitude, could see the sun at 53 degrees from vertical in winter and at 7 degrees from vertical in summer. This is exactly what is observed. So we were able to see that if you're able to stand at one point at that 30-degree northern latitude, we could see at different points of the year it would be the same at different degrees when you're at different latitude and longitude and things like that. And experimental testing. Scientific explanations may be analyzed and evaluated through experimental testing. A well-designed experiment allows you to change one variable to determine precisely how other variables respond. So here we're looking at speed and height, and we have a graph going here with data points on it. Experimental evidence must be carefully critiqued. What are the key questions a researcher should consider when evaluating the quality of experimental results? All right. Experimental evidence must be carefully critiqued. In doing this, is the experiment objective? You're going to see that, is it objective, or is the scientist trying to get to its own outcome? Are the observations unbiased? Make sure that the scientist is only writing down what happens and not what he wants to happen. Could other variables have caused the observed effects? You need to make sure that your variables, like we looked in the last chart, you only had 2 variables going there. Are there any other variables that could affect the results? Do other researchers observe the same result? So once you publish your results, others are going to do the same experiment and see if they get the same results you did. Has the data been analyzed to understand the uncertainties in measurement? Are the observed effects greater than the uncertainties in measure? There are uncertainties in everything that you do because some measurements might be off by a little bit. That's why we give a plus minus a lot of times when we give answers in science. It'd be plus minus 1 or plus or minus 2, or it might even be a decimal point. All measured data contains some degree of uncertainty. This uncertainty or error is the unavoidable difference between a measurement and the true value of the quantity being measured. But if physics is based on measurement and all measurements contain uncertainty, then how can we ever be confident about scientific explanations based on the experimental evidence? This is a very good question. Let's say a student wants to test this scientific explanation. Heavy objects fall faster than light objects. He drops a heavy stone and a light stone and collects this data on the time to fall. So we look over to the right and you see mass 1 takes this amount of time to fall, and then mass 2 has this another column of time to fall. The student argues that this data supports his explanation. His friend says he's wrong. What is the evidence for each of you? Who is right? So let's take a look at this. Ask yourself, what is the observed effect? What is the uncertainty in the data? What caused the uncertainty? Is the observed effect significant compared to the uncertainty in the data? So several questions here we need to take a look at. The experiment does not support the explanation because the experiment finds no significant difference between the heavy stone and the lighter stone. The values for the heavy rock vary by more than 1/10 of a second. The average value for the 2 rocks differs by only 2/100ths of a second. If you see the averages down here. Uncertainty can never be eliminated. Taking lots of data allows you to quantify the uncertainty. Empirical evidence must also be evaluated with respect to uncertainties before any conclusion can be made. So here you go with a number of measurements, the mass 1 and mass 2. You see you got 0.68, 0.78, 0.88. 0.70, 0.80, 0.90, and you basically have your measurement errors. All right, logic. Well, how do you know a statement is true? How is a scientific argument made? The if-then structure is one of the main ones that science uses. If Earth is round, then it should be possible to travel in the same direction and end up back at your starting place. Many steps in scientific inquiry use this kind of reasoning. It is a way to propose potential consequences of a theory being true. A proposed consequence is an observable test for the truth of the theory. If the consequence is actually observed, the theory is supported. If the consequence is not observed, the theory is known to be at least partly incorrect. That's pretty important there, that partly incorrect. You might just have part of it wrong, not the whole thing wrong. Here's more logic. Why do things happen? Why do they actually happen? We believe that things that occur have causes that may be understood by humans. This is called a cause and effect relationship. That's why things happen. Something caused something else to happen. Objects start to move because unbalanced forces act on them. Many explanations in science use this kind of structure. The effect is something that happens, Things start to move. The cause explains why or how something happened the way it does. An unbalanced force acts on it. All right, we made it to our assessment question. State in your own words the definition of science. Include the following ideas in your answer: evidence, testable explanations, predictions, natural phenomena, and knowledge. Think about this for a second, and you can pause the tape here because I'm going to be moving on. Okay, your answer will vary somewhat, but science is the use of evidence to construct testable explanations and predictions of natural phenomena, as well as the knowledge generated through this process. You see an icicle hanging from a branch of a roof and notice that the ice forms in ripples on the surface of the icicle. Which of the following is a valid way to test a hypothesis about these ripples? Do research for information on the internet. Look for information in textbooks or at a library. Ask a teacher or another knowledgeable person. Do an experiment by creating icicles at different temperatures. What do you think it is? And the answer is do an experiment by creating icicles at different temperatures. And I'll let you know this, in just about every standardized test out there, if there is a question or with an answer that says do an experiment, that's pretty much where it falls. Because experimentation is big in science, and that's what the main thing they're looking for scientists to do and students to do is to do an experiment. Which of the following could be scientific evidence? The speedometer of a car reads 57 miles per hour. A photograph shows the planet Venus at a specific position in the evening sky. A newspaper headline announces the discovery of a previously unknown fundamental particle. You notice that the temperature outside is 27 degrees Celsius. A teacher tells you that the atomic mass of carbon is 12 grams per mole. And here you go. The speedometer of a car reads 57 miles per hour is one. A photograph shows the planet Venus at a specific position in the evening sky. And then you notice that the temperature outside is 27 degrees Celsius. How did Penzias and Wilson contribute to our knowledge of the origins of the universe? Hopefully we wrote this one down and we can look back at it. In 1964, Penzias and Wilson used a microwave antenna to measure the universe's temperature. Their findings matched the temperature predicted by Alpher and Hermann in 1948 and confirmed the Big Bang theory. This was in that area where we looked at where they came up with the theory of the Big Bang, and we ended up with our galaxies theory. A lot more of this is explained in the book, which I'm always going to say, read the book.